So hello everyone, my name's Nick Evans. I'm actually the head of the Theoretical Particle Physics group down here in Southampton. What I'm planning to do today is to do an introduction to particle physics. I actually spend most of my time thinking about the strong nuclear force and a little bit about string theory, but we'll come on to that maybe in the discussion session later. So I'm going to do a first introduction to particle physics, and then Ken will come in and talk you through how to actually understand particle physics events with a bit of a hands-on exercise that you can get involved with. So let me share my slides. Okay, so hopefully you can now see what I'm going to talk about. So what I want to try and do is to introduce you to the main bits of theoretical thinking that underlie particle physics. And then I'll go on and I'll talk about the latest discovery in the field, which is now sort of 10 years ago, which was the Higgs boson, and the Large Hadron Collider, which was what we used to find that. And then I'll talk a little bit about what we're expecting in the future. And then, as I say, Ken will come in and look at some events with you in colliders and teach you how to interpret them. Okay, so what's particle physics all about? Well, we're the ultimate in reductionists. We like to chop the world up into the smallest possible things we can find and ask, what is the universe made of at the very smallest scales? So what are the particles of which the world is made? How do those particles interact? And then there's a hope that eventually we will come to understand why it is that the universe has to be this way, and perhaps also understand some of the cosmology of the universe, about why the universe started in a big bang and so on. But those are really quite speculative questions. And for the moment, we'll satisfy ourselves with just working out what the universe is made of. Okay, so where's our understanding? Well, first of all, if you look around the room around you, it's remarkable what a simple explanation we have of all of this stuff about you is. Because fundamentally, we think that this material is all made of atoms, and atoms are fundamentally made of just three sorts of particles. So I'm sure most of you already know this. So you can think of an atom as being like a mini solar system. There are electrons, like planets, in orbit. They're held tied to the central sun of the atom, which is the nucleus, which is positively charged. By the electron's negative charge, the electric attraction keeps them in those orbitals. So the electrons are the example of what we believe at this time is a fundamental particle. That means we've never managed to break one up or see any structure in it. We think it's a fundamental thing. And I like to joke that the whole of the rest of science is really about the study of electrons. So, for example, if you look at things, you're interested in the emission of light. That happens when electrons change their orbitals within an atom. So if they fall in closer to the nucleus, then that's energetically favorable and they give light out. If they absorb light, they tend to move to orbitals that are further away from the nucleus. Okay, so light is, and looking at things is all about electrons. Electricity and magnetism, well, that's about moving electrons. If they move in a straight line, then you get a current. If they move in a circle, then they generate a magnetic field. And that's sort of all of electricity and magnetism. And of course, then there's electronics, which is about understanding how to manipulate electrons to make interesting gadgets and so on. Then there's chemistry. Chemistry is all about when you bring two atoms together, how do the electrons change their orbitals to reflect the fact that there are now two nuclei that they can potentially orbit around, and that causes bonds and so on. And similarly, the mechanical properties of materials is all about how the electrons interact in those materials. So then I would claim that particle physics is sort of unique, that we look at the other two particles of which stuff is made. We look at the nuclei of atoms, which, as again, I'm sure you know, are made of protons and neutrons. So protons are positively charged, neutrons are neutral, but they all stick together by something called the strong nuclear force, which is a force which is about 10,000 times stronger than the electric forces, which is why they are crunched down into a bit of space about 10,000 times smaller than an atom down there at the center. Now, in the 1960s, we started smashing up protons and neutrons, and we came to realize that basically the difference between protons and neutrons corresponds to the fact that they are made of things called quarks or quarks. And there are two types, which are called up and down quarks, rather prosaically. So a proton is made of 2 up quarks and a down quark, whilst a neutron is made of 2 down quarks and an up quark. And you can see I've put the electric charges there that add up to correctly give you the proton and neutron charge. So remarkably, everything that we know in the universe basically is made of those 3 particles. But I'm going to add one extra guy into the mix, which is something called the electron neutrino. So this is another guy which is sort of just about part of the universe that we see, and that's because it's involved in radioactive beta decay and also fusion in the sun. So in radioactive beta decay, a force called the weak nuclear force, which is quite a strange beast, causes neutrons to convert to protons. So that doesn't conserve charge, but then an electron is emitted as well. And in the early days, people thought that was what the process was, just neutron decay to a proton and an electron. But then they started studying that proton and electron, and they found that interactions didn't conserve energy and momentum. So if you start basically with the atom at rest, you'd expect the proton and electron to come out in opposite directions, roughly with equal energy. But that isn't what you find at all. And eventually, the only way that people could explain it, it was explained by a physicist called Pauli, was to say that in that interaction, another particle must be coming out as well that we then don't see. So that's a particle that has no electric charge, so we'll never interact with it by emitting or absorbing photons of light. And it doesn't get involved in the strong nuclear force, so it doesn't get sucked into the nuclei of atoms. So if we assume that's there, then we can make energy and momentum be conserved in these decays. But it took a long time for people to actually see these things, but now we can. So how do you see neutrinos? Well, you need a detector, and for example, over in Japan, they've hollowed out a mountain and filled it with a swimming pool. It's called the Super Kamiokande experiment. Round the edge of the swimming pool, which of course is very dark in the middle of the mountain, they put photodetectors. And what they're looking for is anything that interacts in that water, the protons and neutrons in that water, will eventually emit some light, and then they look for those flashes of light. So you then need a very strong source. So I should stress that these neutrinos are really very weakly interacting. They can actually go for light years through lead without interacting. They only interact by this very, very weak nuclear force involved in beta decay. And so you need a very strong source, but luckily we have one, which is the sun. In the sun, protons stick together, and then some of the protons become neutrons by the reverse of beta decay, and that's how hydrogen becomes helium in the nuclear fusion processes. Light is given out in that process, but also a lot of neutrinos. And what I've shown you on the right here is a picture of the sun in neutrino light. So that's taken at Super Kamiokande by waiting, well, several weeks looking for incoming neutrinos from the sun in their bath of water. Okay, so we've got 4 particles of nature that make up basically everything that you and I have ever interacted with. So up quarks and down quarks make up the nuclei of atoms, electrons in orbits around them, and then these neutrinos that can be produced in these weak force processes. Okay, so how do we describe these particles? So now I want to talk about some of the theories that we've developed that play a crucial role that will bring us on to sort of the techniques we use in particle physics. And the first one of those is relativity, discovered by Einstein about 100 years ago. And it all rests on the idea that the speed of light is the same for any observer. Now that seems like a very sort of small statement from which not too much would follow, you would think, but actually it's really quite revolutionary. So let me try and tell you about some of the effects that it has. Okay, so the first thing is that if the speed of light is the same for everyone, it means that nothing can travel at the speed of light. So if you think about some light traveling across, in front of you, if you could travel at the speed of light, you would be able to run along with that light and it would look stationary to you. And yet this statement, which turns out to be true for our universe, says that's not possible. And therefore, this means that nothing can travel with light. And that means that you have to go in, this is what Einstein did, and change the laws of physics that you've been taught at school. So at school, you get taught that if you kick something, it accelerates. If you kick it again, apply a force, it accelerates again. And you can keep on doing that until it's going as fast as you want. So that can't be true. There must be a maximum speed limit of the speed of light. And so Einstein had to come up with a formula to encapsulate that. And that's the one written here, which you've probably already noticed has E equals mc squared sitting in it, which is what the famous one that you know. But that isn't what Einstein was trying to do at all. He was interested in this square root factor, but I've put out the front, which people don't normally show you. So the point here is that V is the speed of the particle and C is the speed of light. So if V equals C, what we get on the bottom there is 1 minus 1, which is 0, and then we're dividing 1 by 0. That's an infinite number, and it doesn't matter if you square root it. So what this formula does for you is it says that nothing can travel at the speed of light, because for you to be able to make it do so, you would have to give it an infinite amount of energy. Okay, good. And then Einstein said, oh, and I better just check that when things are stationary, that they don't have any kinetic energy. So he then set V equal to 0 in this formula, expecting to get 0. But instead, what you get is that that square root factor just disappears. It just becomes 1. And you're left with E equals mc squared. And suddenly you understand that the rest mass of a particle is a reflection of the energy, of some energy that is stored in it. And we use that in particle physics to make particles. If we can cram enough energy into a small bit of space, then the universe can choose to convert that energy into particles. Okay, I should say, incidentally, I've seen that we've got some questions already. We'll store those up and we'll come back to them at the end of this talk and then in the chat session later on. So thanks for those. Do keep putting them in if you think of them. All right, the second thing about the speed of light is the same for anyone. Again, sounds innocuous, but it's really quite bizarre. So what I want you to think about on this slide is that there's a flash of light somewhere. You can think of it as, you know, a lighthouse giving off a flash of light at some point. So the lighthouse keeper is sat at the center of where that light came from, and he sees light go off in all possible directions at the same speed. And so after some time, he will see the light as though it's spread out over the surface of a sphere, which I've drawn here as this purple blob centered on the light flash, the star. Okay, so that's all fairly straightforward. But what now about somebody who's in a speedboat? So this is a very fast speedboat, which is whizzing past. And it happens to pass the lighthouse just as the light flashes. So from the perspective of the guy in the boat, a flash of light happens where he was, and then he sees it go off in all directions at the same speed. And that's true independent of the fact that he's then moving. So of course, later on, the guy in the boat is separated from the lighthouse by some distance because he's moved. And yet that guy in the boat thinks that the light is spread out in all directions equally and therefore is on the surface of a sphere, now the green one, centered on the boat. Well, this is mad. How can it possibly be that these two observers, the lighthouse keeper and the person in the boat, see completely different things as to where the light is? Well, remarkably, it turns out it's true in our universe that that is the case. And the reason is that moving people see space and time differently. So you have to think about when things happen. So, for example, the light passes this point here. And you would give that in one of these frames of reference, as they're called, one of the observational setups that these people have, you would give it some coordinates. You would say it happened at position X, Y, or Z, and at time T. But it turns out that the two moving people disagree about when those times are. So I'm not going to go through the details of this, but I've written the equations which just show you that the moving person's time and space with primes on are not the same as the static person's T and X. And they differ depending on the speed of light and the speed that the person is moving at relative to the speed of light. And in particular, what happens is that people disagree about what things happen at the same time. When this lighthouse keeper says the light is at the top, at the bottom, at the left and the right of that purple sphere at the same time. He's saying the light reaches each of those points at the same time. But the person in the boat disagrees. He thinks that the light reaches the point on the right of the purple sphere before the light reaches the edge of the purple sphere on the left. So they just disagree about when things that are separated happen. All right, so one can spend a lot of time thinking about that, and we don't have time for that now. But what I want you to take away from that is just the thought that two moving people disagree about when things happened. We'll come back to that. Right, the other theory that we need as part of all of this is quantum mechanics. So this is the theory that kicks in when you get down to atomic scales, that describes how particles behave. And what turns out is that, again, the laws of physics we teach you at school, Newton's laws, stop working and a new set of rules come into play. Now, there are two aspects to this. One is that those rules stop being deterministic completely, right? If you know the starting point of a particle in Newtonian mechanics, you know where it ends up. If you know where it is and how fast it's going and how much it accelerates, that's all you need to know to work out where it ends up. But in quantum theory, that's not the case. What the theory gives you is several possible answers for where the particle might turn up, and each of those comes with a probability. And that actually necessarily means that you end up with a wave description of those particles' behaviors. Because if you think about having many particles and you send them out with the same initial conditions, they end up in different places. And then you can sort of think of the density of the particles at different endpoints as looking like a wave. So I've drawn a wave here, and you can just think of this as where the wave is big, there's likely to be a lot of particles. Where it's zero, there won't be any particles at all. So if you have a lot of particles, all, as I say, with the same initial conditions, but ending up by quantum mechanics in different places, you necessarily get things that look like waves. And then there's another way of describing quantum mechanics where you just describe the waves themselves. When you do it that way, it turns out that the energy in the wave isn't distributed uniformly like you would think if it was a light wave, but actually you naturally find that it comes in little lumps. So you maybe know that the energy in a photon is given by Planck's constant, about 10 to the minus 34 joule seconds times the frequency of the light. So this is the particles. They're sort of the energy that make up that wave. If you get it down to the last lump of energy in the wave, then that thing actually looks like a particle. And as I say, photons are the name that we give to the particles in light. So another way of thinking about this is that you can try to follow one of these particles through an interesting and complicated experiment. Well, it's not that complicated, so it's a double slit. I have, say, a light source or an electron gun, and I fire it at a piece of paper with two holes in it. So these holes just replicate twice the source. And then what you find on the other side is that if you think about it in terms of waves, it's just like waves, water waves going through two holes in a barrier. You get an interference pattern where there are constructive interference where peaks meet, destructive interference where a peak and a trough meet. And so you get a pattern for the final wave, which is like this yellow pattern where there are peaks and troughs. And that means that you're more likely to find the particle where the peak is, less likely where the trough is. Okay, fair enough. And that's what happens if you put lots of particles through. You just see that distribution of the density of particles later on in the experiment. But what happens if you turn down the intensity so that there's only one particle at a time in the experiment? Well, the wave still says that where it ends up is determined by this wave, and the probability is basically the height of the wave. But what happens to that individual particle? What if I stand by this hole at the bottom and say, I'm going to see whether the particle went through it or not? Well, the answer is that the way that the particle dynamics gets changed is by something called the Heisenberg's uncertainty principle. So let me use the one at the bottom here, which says that over a very short period of time, And this is roughly the time that it takes for an electron to cross an atom. So it's really quite a short period of time. There's actually a fundamental uncertainty in our universe as to the energy of things. And that uncertainty is controlled by this constant, Planck's constant. It's very small. That's why this only happens over short timescales. But if we go back now to the double slit experiment, then one way in which you can understand it is that if you actually sit there and check that the particle goes through that bottom slit, you know, at some point during the experiment, so you've timed it, you've said, yes, it's gone through, then that act of putting it into a little time zone for when it went through the slit enacts the Heisenberg's uncertainty principle and actually gives that particle the ability to borrow energy that you didn't know about. And in fact, it's enough energy that it can basically then nip back round and go through the other hole while you aren't looking. So this uncertainty principle is really how Newton's laws changes in quantum mechanics. That everything is a little bit fuzzy, and it's a little bit differently fuzzy for different particles, which is why different initial conditions can end up in different places. All right, so those are our two theories that we have to put together. And what I now want to do is do what Paul Dirac did back in the 1930s, late 1930s, when he first put those things together and made a remarkable discovery. So he was thinking about electrons absorbing photons. So here we have this white line is supposed to be an electron, and then the yellow wiggly thing is a photon that comes in, and the electron absorbs it, takes the energy from that photon and scatters in some way. Okay, well, that's all perfectly sensible. But then Paul said, but look, in relativity, different observers who are moving relative to each other can disagree about the order in which things happen when those events are separated. And he wondered what would happen if you found somebody who thought that the particle going out sort of came out before the particle that was going in came in. So basically, it's just rotating this diagram in space and time to get the diagram that we have at the bottom. So he imagined that the particle could sort of come along and then scatter backwards in time. Well, you know, this seems crazy, right? But then he thought, well, let's try and think about what that would actually mean. So think about putting an electron in front of you on the desk, and then let's draw an axis upwards, which is time. Over time, it sort of moves up in front of you, right? It's at the same place, but it's moving through time. Now imagine you could take an electron and you could sort of put it in the future at the end of that process, so up at the top of the line, and then send it back down to where the starting time was. So it's going backwards in time. Well, all I can say about that is that the electric charge of that electron of one guy went forwards in time, but then an equal amount of charge went backwards in time. Well, I don't want to talk about going backwards in time. I don't know what that means, but what would that look like to me as I go forwards in time? Well, the result is that no net charge has gone forwards in time because the stuff went forwards, but another guy went back. And so the natural way to understand this is that the guy going backwards in time actually looks like a positively charged particle going forwards in time. And so this is what Paul Dirac proposed, was that every particle necessarily in relativity should have an antiparticle, a particle that's identical in all respects, but its charges look opposite because it's sort of secretly moving backwards in time. Okay, and of course, you know, everyone went, oh, theorists, they come up with their crazy theories. This is clearly mad. But then people started sending bubble chambers, so particle detectors, up in balloons to the surface of, to the top of our atmosphere to look at radiation coming in from the sun. And amongst the things they found were things that looked exactly like electrons, but they spiraled the wrong way in a magnetic field. So charged particles tend to go in circles in magnetic fields, but you should know which direction they go by their charge. And so these things going the wrong way looked exactly like positively charged electrons. We now call them the positron. They're the antiparticles of the electron. Paul Dirac was right, relativity was right, and now we know that every particle in nature has an antiparticle. Okay, we've now got all the tools that we need to do particle physics. So in particle physics, what we do is that we take an electron and a positron and we annihilate them into energy or a photon, as I'm showing here. But of course, you can think of that, if you like, as an electron scattering backwards in time through the interaction with a photon. So it's just like the usual sort of interactions, just sort of turned skew width in space-time. Okay, once you've put all of that energy into the photon, now nature can use E equals mc squared to make new particles. So the first thing it could do is just to remake an electron and a positron. That would be perfectly fine, and that happens. But it now has the ability to make any particles that have charge and that it has enough energy to produce. And so this is what particle physics has been doing for getting on now for 100 years, is that we keep building higher and higher energy collider machines that bring, say, that electron and positron together with more and more kinetic energy, as well as their rest mass energy, cram that down into a tiny bit of space, and then just say, okay, we've given you some more energy than you've ever had before. What can you make? And that's the scheme. Basically, over time, we are scanning through energy scales, looking for what all the particles that nature is made up of. All right, so what have we found? Well, we've found a lot of puzzles over the years, and I'm going to briefly do the puzzles, and then I'll talk about something that we've solved, so that's more fun. So what did we discover? The first thing we discovered was a heavy version of the electron called a muon. Now, it's exactly the same as an electron. It has all the same interactions, except it's 207 times heavier. And if you make one, after about 10 to the minus 7 of a second, it decays away and becomes an electron and neutrino, basically by the weak nuclear force. So these things don't hang around. They're not part of everyday life, but you can make them. Okay, actually, one of the neutrinos that is produced is called a muon neutrino. It's the muon's version of the electron neutrino. Then we found a third copy. It's called the tau, or the tauon. Again, it's exactly like an electron, has all the same interactions as far as we know, except it's about 20,000 times heavier. It has a neutrino partner as well and decays away very quickly. And over time, we've come to realize that all of the particles of nature have this threefold replication. So there are versions of the up quark called the charm quark and the top quark, and versions of the down quark called the strange quark and the bottom quark. But they're just identical particles, except they have different masses. We actually have no idea why nature has chosen to have 3 particle copies. We suspect there are no more for various reasons that we can discuss later. Why? Why does it need them? You know, they all decay away in day-to-day life. They're not part of our universe really at all now, but we can make them in our colliders. Okay, so we don't know the answer to that. And we don't know why these particular particles with these particular charges exist. However, we have managed to solve one puzzle. And that puzzle is, how do identical particles have different masses? And this is very confusing. So if you think now that mass is energy, this means that these particles have different energies. But energy is all about interactions, right? Think back to those atoms. When they absorb energy, they go to a higher orbital. When they emit energy, they fall in towards a lower orbital. This is all to do with the attraction between the electron and the positively charged nucleus of the atom. So if they have the same interactions, how can they possibly have different energies associated with them? So this was the big puzzle that people were working on for 40 years until 10 years ago, when we started to find the answer. And the answer is the theory that Peter Higgs and Englert and Brouwer as well were involved in constructing. It goes by the name of Peter as the Higgs boson. And this is how we believe that masses are formed in our particle physics system. So the key thing is that there must be a new force that is responsible for the energy of the particles. And furthermore, that force must be happening everywhere in space, the same everywhere, right? Because an electron's mass doesn't change depending on where it is in the universe. It's the same, and therefore it suggests that all the way through space, it's having some sort of interaction with some background field that it's interacting with. So this is the idea of the Higgs field, that the whole of space is filled with some substance. You can think of it as being like an electric or a magnetic field that fills space. And the particles are constantly interacting with it, generating the energy that is their mass. So a few years ago, there was a little cartoon explanation for this, which was produced by a guy called David Miller. This was back in the days when Margaret Thatcher was Prime Minister, and her science minister wanted to know why we should build the Large Hadron Collider. And this was his explanation of how the Higgs mechanism works. So the idea was that this is some big, I think actually it was supposed to be the Conservative Party conference back then. So there were lots of Conservative Party MPs milling around in the conference. And then somebody famous, you can think of it as Boris Johnson or Margaret Thatcher or whoever, comes walking into the room. And of course, all of the MPs think they're very important and want to go and talk to them. So the background of MPs reflects the field everywhere in space. And now the Prime Minister or whoever it is walking in represents a particle. And now because there's this clustering and interaction, as shown on the top right here, between the MPs and the Prime Minister can no longer walk at the same high speed through the room, but is slowed down. It acquires energy and mass, is the analogy that's being made. Okay, so that was basically what Peter Higgs wrote in his original paper. And the referee of the paper refused to publish it on the basis that, how do we know? This could just, what you've basically said is there's stuff out there, fairies or something, and fairies give mass to all the particles by this interaction. How do I know if the fairies are really there? So Peter had to go and sit down and scratch his head and think of another way in which you could see this. And the bottom two graphics are supposed to illustrate what he proposed. So here the idea is that someone comes to the door, maybe from the Labour Party, and whispers, Boris Johnson's here, and everyone gets very excited, and there's a little clumping around where they think that Prime Minister or whoever is, when there isn't anyone actually there. This is the idea that if you can inject enough energy into empty space, you can disrupt that background and make a little clump in there, and the smallest lump of energy in quantum mechanics that you can put in is a quanta, a lump of energy called the Higgs boson. And so this is the idea that we've had, that if we could put enough energy into a small bit of space, we could disrupt the background that is everywhere throughout the universe and see that this thing is present. So this was the basic idea of the Large Hadron Collider, the experiment that we built in Geneva. So this picture shows you, top right is Lake Geneva, the bottom left is France. The white line shows you where about 100 meters underground there is a 27-kilometer round tunnel, and that's where the Large Hadron Collider is based. So it's underground so that we don't irradiate the people in Geneva or anything like that. Okay, and it's been going since 2009, so let me tell you a little bit about it. So that's a picture inside the tunnels, and basically in that tunnel there is just a beam pipe, so it's a circular pipe going around. There's a vacuum in there so that you can send particles in there and they can just whiz along without interacting with anything. And then every so often around the loop there's a station where you can use an electric field to give them a boot, and then they go to higher energies. And so you slowly speed them up as they go around the machine. To make them go in a circle, you have magnetic fields. So you have to have a lot of big magnets. So there's about 1,200 35-ton superconducting dipole magnets over there, which are just there to, focus the beams and so on, but basically just to get them to go into a circle. To make those work, you actually need to get them cooled down to near absolute zero, so 2 degrees Kelvin. So there's actually 36,000 tons of liquid helium coolant in those tunnels, which at least at one point was over half of the liquid helium on the planet was being used in Geneva. So the idea is that you take some bunches of particles. Now, in this case, actually what we use is the cores of hydrogen atoms, in other words, protons. It turns out to be easier to accelerate those and keep them going in a circle. And what we've done is we've accelerated those to an energy which is 10 times higher than we'd ever managed before, so that when they collide, proton on proton, there's enough energy just from the kinetic energy to make about 14,000 protons worth of mass. So these are really very, very high energetic collisions. I mean, it takes quite a lot of expertise. I'm a theorist, so I can't take any of the credit. But, you know, to make these things, these beams collide, you have to worry about the tides and the metro in Geneva and all of these sorts of things. But they managed to do it. They managed to make these guys collide. Okay, so you might then ask, well, okay, so you set this up and you collide these things once, and is that it? You then see what happens? And the answer is no. I mean, particularly colliding protons is a messy business, because they're each made out of 3 quarks. When they collide, most often they sort of just have a glancing collision, and lots of things made of quarks come out. So, you know, in this picture on the left, you can see all sorts of showers of stuff happening. And most of it isn't very interesting. Mostly what you're interested in is a very, very special collision where one proton has one quark with most of the energy, and another proton has all the energy in another quark, and those quarks hit head on. So you can really use as much of that energy as you want to try to make new particles. So to do that, you actually need a ridiculous number of collisions. So in fact, what they collide is bunches of about 100 billion protons, which sounds like a lot, but relative to the number of protons in your body is a tiny amount. When those bunches go through each other, there are typically about 20 collisions every time the bunches cross. And they are then pretty much now up to the point where they're doing a crossing every 25 nanoseconds. So they're generating 600 million collisions per second. That is a huge amount of collisions. In fact, given that any individual one of those will give you a picture like this one on the left, that is more data than it's possible for humanity to store. You just can't write that to tape or to CD or whatever fast enough. So you have to have some very clever electronics which processes those collisions and actually throws most of the information away. So in particular, if all that happens is a glancing collision and there's lots of stuff made of quarks and nothing particularly high energy comes out, we don't even look at it. The experiment doesn't let us. What we're looking for is very, very special events where things come out which carry a huge amount of energy, whether it's electrons or muons or photons or something like that. Particularly if it's something that isn't quarks, which is then really easy to distinguish from all of that other background material. Okay. And how do we get those pictures? Well, you know, tiny little collision, right? Things down at 10 to the minus 17 of a meter. But then the sprays from those typically go, well, about, you know, across the size of a thing, about the size of a house. So we have detectors. The two famous ones are ATLAS and CMS at the Large Hadron Collider. And they basically consist of an area around the collision point where you can track the particles that are coming out. So you just can literally draw lines to see where charged particles are. And then surrounded that are layers of lead in which you try to stop the particles and work out how much energy and momentum they had. So this Ken will tell you a lot more detail on shortly. So I'll not go into any more detail than that, other than to just show you the pictures. And, you know, you can see a ladder on the end of the ATLAS experiment there to get some sense of the scale over which these pictures are taking place. Supposed to start up in 2008, so this is all ancient history now. There was actually originally a welding problem on one of the magnets, which caused a very, very small spark to happen. But unfortunately, that triggered a release of the liquid helium. And when you release liquid helium, it heats up and becomes helium. And so they flooded the tunnels with helium gas, as well as causing quite a big explosion in the process, which did this rupturing shown at the top to the beam pipe. So they had to go and rebuild. But then in 2009, they got things going. And again, these are sort of what the outputs of events look like, where for the moment, you should just sort of take that as meaning, look, there are streams of particles coming out, and then you've got to try and interpret what those means. And I'm going to hand on to Ken, and he will try and teach you how to understand what these sorts of events mean. Okay, so then we come to about 2012, which was the point where we actually succeeded in discovering this Higgs boson particle. So remember, what we were trying to do was to put lots of energy into a very small bit of space to excite this background field, this Higgs field that we believe is giving mass to all of the particles. So one of the ways that that Higgs field would show itself to us, so it won't stay around as an excitation for very long. It'll decay back into normal stuff. And one of the decay channels, which was very early to be seen, was it decaying into 2 photons. So that's what this picture at top left is showing you. The collisions come in from the left and the right. The orange things are just lots of quark matter spray. But the green things are basically 2 beams of laser light, 2 photons coming out of the center of that collision. And what they do is just look for those and then add up the energy of the 2 photons and see what it adds up to. So these little plots, they're called Brazil plots with the green and yellow after the Brazilian flag, are basically on the left. You should just think of that as saying, how many particles are you seeing? It's actually relative to how many you expect to see, and against the energy that you get when you add them up. And it turned out that, so I think, let me see, yeah, so this one I think is the photons, where you see that there's a peak of 2 photons coming out at about 125 times the mass of a proton. And then they also looked for other channels where, for example, the Higgs can convert itself into 4 electrons or 4 muons. And again, they saw a peak they weren't expecting without the Higgs, sat around 125 GeV. And by adding up over all of these signals, they managed to come up with what they call a discovery, which is a more than 5 sigma. So that's something like 99% probability that you're not seeing something by chance. And so they could say, look, we really are producing something new in this experiment that's decaying in these ways, and it's consistent with the Higgs boson being present in this experiment. This was the meeting at CERN where it was announced, and Peter Higgs then duly got to go off to Norway and get his Nobel Prize for the discovery. Okay, so that's been the big discovery of the last 10 years or so in the field. We had this idea that particles had to have a new interaction. There had to be a new force with this material that fills the whole of space. We've now managed to excite that and discover that it's there. So what follows on? Well, what follows on is starting at least to test it really carefully. We want to know, is it true that the coupling between those Higgs bosons and, say, the top quark, which is the heaviest particle, is bigger than the coupling to the bottom quark? In other words, is the force different dependent on the forces of the mass? And those are the sorts of things that we're checking at the moment. And in fact, the LHC is due to run until 2040 or so. So at the top left here, I'm showing you, so the green periods are the run times, the blue periods are shutdown times. So, you know, you run it for a while and then you tend to burn things out and you have to go in and replace bits of your detectors or try and put it into a different configuration where you'll see more events over time and so on. But there's a lot of time to go. And if you look at the bottom, I'm basically plotting the number of events here against time. It's probably a bit small for you to see. But this was the early run up to the discovery of the Higgs boson. And now in the 2022 run, they got up to, well, you know, about 10 times as many events as they had at that point. So all the time we're getting the precision on all of these measurements. Our ability to see rarer things is getting greater and greater. So what have we found today? Well, what we found today is that our standard model, which is all the particles I've talked to you about and the Higgs boson, is standing up really pretty strongly. So again, you don't want to know all the details, but there are many, many things that are measured, all of these little things on this chart or down this chart. And what we can do is to make measurements of them and compare them to what the current standard model, our theoretical model of these things should be. And at the moment, it's standing up really well. We haven't seen any deviations from what we were expecting. So that confirms the experiment we've got, confirms the theory that we've got, but we're hopeful that we'll yet find more things. So what other things might we be looking out for? Well, you know, for example, I said that there were 3 generations of matter. Could it be that suddenly we'd have enough energy to produce a 4th generation? Astronomers are out there. They're really worried that there's a whole bunch of things in the universe that interact by gravity, but they don't know what they are. They call it dark matter. Could it be that suddenly we would be able to create those particles in our accelerator? Maybe there'll suddenly be new forces between the particles we know. Perhaps the electron will suddenly break apart into multiple things. The Higgs is the first example of a spinless particle that we found. So all the other particles are like little tops that are spinning, but the Higgs isn't. The Higgs particles are just sit there like points. Are there other particles like them? So I talked about matter and antimatter. In particle physics experiments, if you ever make matter, you get an equal amount of antimatter. And yet here we are, we live in a universe which is dominated by matter. So we need at some point to see interactions that favor matter over antimatter. Maybe we could see those. Or then there are more crazy ideas like extra dimensions of space or new laws of motion. You know, maybe quantum mechanics will break down or so on. All of these are possible things we could see. And now we just have to run this machine for the next 20 years and see what it is that comes out, and hopefully exciting things along these lines. All right, so I am basically done at that point. I hope I've convinced you that we have a concise description of matter and forces, right? I mean, the fact that around us is made of just 3 particles always amazes me. They do have some strange laws, relativity and quantum mechanics, which if you're interested in studying, you'll want to come on to university and study physics to understand those laws. We have to put those together to explain everything that we're seeing. The big missing element sort of 10 years ago was understanding how different particles could have different masses even though they have the same interactions. We proposed there was a Higgs field, a new force that would explain that difference, and we've gone out and we found it, and that's great. But there are still all those questions we can't answer, like why is there a 3-fold replication of matter? Why do the particular particles with their particular charges exist? The other thing that people always mention, of course, is that we ignore gravity in particle physics experiments. Gravity is unbelievably weak. You can get out of bed with just the electric forces in your body resisting the gravitational attraction of the whole of the Earth. That sort of shows you how weak the force is. So in these particle accelerators, we just don't see gravity. It's such a weak force, we can't say anything about it. So at the moment, we don't have a theory about how gravity interacts with particles. Anyway, we're hopeful that the LHC will take us on a ride yet to discover new things. And so on that point, I think I shall come to a pause.